You can write a first order ordinary differential equation for the terminal velocity of an object. So for terminal velocity, we're going to have the sum of forces on a falling object is how we're going to make that differential equation. So the first thing is we're going to have drag, and this letter here is a gamma, Greek letter. I tried to draw it as best I could. So drag gamma is proportional to velocity. And so that's a reasonable approximation for atmosphere. A better approximation, for instance, in water is velocity squared. All right, so let's go ahead and set up what our different symbols are going to mean. So we're going to have the Earth, we're going to have our object, and positive velocity is going to be going upward. Sometimes people will define positive velocity as downward. It's more convenient for the problem. I find this a lot less confusing, that positive velocity is upward. All right, we're going to have the function v of t is the velocity at time t. We're going to be working in meters, seconds, and kilograms. The next thing we'll need is Newton's law. So we have force equals mass times acceleration. And I'm going to say, mass times acceleration equals the sum of all forces acting on the object. All right, so now we have to go in, we have to figure out all our forces. So there are a couple cases here. So if you have positive velocity, we want to check we are getting everything right. So we're going to have positive velocity case, and we're going to have negative velocity. All right, so we have our ball, and we've got positive velocity, so we have v of t is greater than 0. All right, for here we'll have a negative velocity, so we'll have v of t is less than 0. All right, so now we have one thing operating on the object at all times. It's the gravity of the Earth. All right, so we're going to use g for the strength of the gravity of Earth. And whether or not we're doing positive velocity or negative velocity, the gravity is going to be pointing down. So let me just draw that. And we have to make sure it's pointing the right way. So we're going to have our mass is going to be a positive number. We're going to have the g, 9.8, is a positive number. So this is actually negative mg, right? It's pointing down. That's the direction of the force. Same thing over here. We're going to have negative mg. Doesn't matter if the ball is moving up or moving down. Now for the drag, it does matter. So if you're at positive velocity, the drag is going to be in the opposite direction of the velocity. So in this case, we're going to have drag is going down. But in this case, we're going to have drag is going up. Right, if we're moving down, the air is going to try and push the ball up. If the ball is moving up, the air is going to try and push the ball down. And so now we're going to try one here. So if we have v is positive, and we have drag, and it's pointing down, and we have the drag, this gamma is the coefficient for drag, is proportional to the velocity, then it should be gamma times v. But then, gamma is going to be a positive number. It's a coefficient. V in this case is positive, so it's actually negative gamma times v when you have positive velocity. But now we want to make sure that actually works when we go over here as well. So if we have drag is negative gamma, let me fix that gamma, v, does that work? We want it going upward. Well, the drag coefficient, gamma, is still going to be a positive quantity. We have a negative in front, but the velocity is negative. So we have negative times positive times negative. That will result in a net upward positive force. All right? So that's going to be the different things acting, and we just wanted to check the positive velocity and negative velocity cases to make sure the drag term was going to work in both, because it just switched directions. All right, from there, we can go ahead and make the equation. So one more thing, we have force equals mass times acceleration. So acceleration, so a of t is going to equal v prime of t. It's the derivative of the velocity. So that's how we're going to complete this equation now. So we're going to have the mass of our object times v prime is going to be, so Newton's law, mass times acceleration equals the sum of all the forces, which is going to be negative mg, and then we're going to have minus gamma v. Oh, let me fix my gamma. All right. Now, one more thing that is a little interesting here, the gamma tends to have somewhat strange units. So if you look at the mass is going to have units of kilograms, B prime is going to have units of meters per second squared, right? Because you took the derivative and its acceleration is meters per second squared. It's going to equal, so the m here again, it has mass of kilograms. The gravitational constant for Earth, that's in meters per second squared. Then we have minus, gamma is going to have somewhat strange units. We don't know what they are yet, but we do know v. V is in meters per second. Right, so if we want all of these terms to have the same units to be able to add them together, then right here we have meters kilograms per second squared, here we have meters kilograms per second squared, here we have meters per second. So the gamma term is actually going to have units of kilograms per second in order to get this all to work out. All right, so just to write that down explicitly, gamma units are kilograms per second. All right, so that's how you form the differential equation, and now we'll do some examples.